Hi, Hola, Bonjour and Salaam. Welcome to Blueprint Bazaar, your go-to place for CAD, FEA, and CFD tutorials explained clearly and practically. In today's video, we're going to simulate one of the most fundamental problems in computational fluid dynamics, flow over a cylinder using ANSYS Fluent. This problem is a classic case used to understand boundary layer formation, flow separation, wake formation, and pressure distribution around bluff bodies. Whether you are a beginner or already familiar with CFD, this tutorial will help you understand the step-by-step workflow inside ANSYS Fluent from geometry creation to post-processing. We'll begin by setting up the geometry. Open ANSYS Workbench and drag the Fluid Flow Fluent module onto the project schematic. Double-click on Geometry to open Design Modeler or Space Claim. Here, we will create a simple two-dimensional domain where air flows past a circular cylinder. Start by drawing a rectangle that represents the computational domain. A good practice is to keep the domain long enough for the flow to develop properly, about 30 times the cylinder diameter in length and 20 times in height. Inside this rectangle, draw a circle at some distance from the inlet, representing the cylinder itself. Let the cylinder diameter be 1 meter for simplicity. Once done, subtract the circle from the rectangle so the fluid flows around it, not through it. After that, assign names to your boundaries: inlet, outlet, top wall, bottom wall, and the cylinder surface. Naming boundaries now helps when setting conditions in Fluent later. Save your geometry and close the modeler. Next, we'll move to the meshing step. Double-click the mesh cell in Workbench to open ANSYS meshing. The goal here is to generate a high-quality mesh that captures the details of the flow, especially near the cylinder's surface where the boundary layer develops. Use a fine mesh near the cylinder by applying local face sizing or inflation layers. The inflation layers are critical because they allow us to resolve the velocity gradients near the wall accurately. Around the rest of the domain, you can use a coarser mesh to reduce computational effort while maintaining accuracy where it matters. Once the mesh looks good, check the mesh quality. Orthogonal quality should ideally be above 0.8 and skewness below 0.25. When satisfied, update the mesh and return to the Workbench project. Now it's time to set up the simulation in ANSYS Fluent. Launch Fluent by double-clicking the Setup cell. Choose two-dimensional and double precision settings, and then click Start. Once Fluent opens, check the mesh to ensure everything imported correctly. Go to the General section. Click Check to confirm there are no mesh errors, and then click Scale if necessary to verify the dimensions are in meters. After this, enable the appropriate physical models. For low Reynolds numbers, below 200, the flow remains laminar, so select the laminar viscous model. If you want to simulate turbulent flow at higher Reynolds numbers, choose a turbulence model like K epsilon or K omega SST. For this tutorial, we'll stick to laminar to keep things simple. Under the Materials section, define air as the working fluid with a density of 1.225 kilograms per cubic meter and viscosity of 1.789 times 10 to the negative fifth Pascal seconds. Then, go to the Boundary Conditions tab. Assign a velocity inlet with a uniform speed of 1 meter per second. Set the outlet as a pressure outlet with 0 gauge pressure. Define the cylinder surface as a stationary wall with no slip condition. And for the top and bottom boundaries, either apply symmetry or wall depending on your setup. Once boundary conditions are defined, move to the Solution Methods panel. Use the simple scheme for pressure-velocity coupling. For spatial discretization, choose least squares cell-based for gradient, second order for pressure, and second order upwind for momentum equations. These higher-order schemes provide better accuracy, especially when capturing gradients around curved surfaces like the cylinder. Then open the Initialization panel, select Hybrid Initialization, and initialize the flow field. This provides a good starting point for convergence. After initialization, open the Run Calculation tab. Set the number of iterations to around 300 or 500 and start the simulation. As the iterations progress, you'll see the residuals decreasing. Continue until they flatten out or reach an acceptable convergence criterion, usually around 1 times 10 to the -5 for continuity and momentum. Once the solution converges, we'll visualize the results through post-processing. Go to the Graphics and Animations section and select Contours. Display the velocity magnitude to see how the flow interacts with the cylinder. You'll notice that the flow slows down in front of the cylinder, where the pressure is highest, and accelerates around the sides before separating to form a wake region behind it. This wake region is where vortices form and shed periodically, known as the von Karman vortex street, a fascinating phenomenon that occurs in real-world flows around poles, bridge cables, and chimneys. Next, display the pressure contours. You'll observe a high-pressure region at the front stagnation point and a low-pressure zone at the rear, causing a drag force on the cylinder. You can also plot velocity vectors to visualize the direction and intensity of the flow, or create streamline plots to see how the fluid paths bend around the cylinder and swirl in the wake. If you want to extend this study, you can perform a transient simulation to capture the unsteady vortex shedding behavior. To do that, enable transient under the solver settings. Set a time step size based on the cylinder diameter and inlet velocity, and run the simulation for a few seconds of physical time. You'll then see alternating vortices forming behind the cylinder, a dynamic and realistic flow pattern. If you want to take this transient analysis further, you can start by determining a suitable time step size using the current number criterion. The current number, CO, should generally be less than 1 to maintain numerical stability, so you can estimate the time step as delta T equals co times delta X over U, where delta X is the smallest cell length in the flow direction, and U is the inlet velocity. For example, if the smallest cell near the cylinder is 0.005 meters and the velocity is 1 meter per second, a time step of around 0.005 seconds or smaller would work well. Once you set that, define the total simulation time to cover multiple vortex shedding cycles, typically around 10 to 20 seconds of physical time depending on your flow speed and domain length. To capture the transient effects properly, enable data sampling for time statistics under the Calculation Activities tab, so you can average pressure and velocity over time later. You can also enable auto-saving for case and data files at regular intervals, for example, every 50 or 100 time steps. This allows you to visualize how the flow evolves, frame by frame, without losing progress. If your computer supports parallel processing, use multiple cores in Fluent to speed up the transient run, since this type of simulation is computationally more expensive than steady-state cases. Once the transient simulation begins, you'll notice oscillations developing behind the cylinder. Over time, these oscillations grow into distinct vortices that detach alternately from the upper and lower sides of the cylinder, forming the well-known von Karman vortex street. To visualize this, go to the Animations panel and create an animation for velocity magnitude or vorticity contours. Setting around 100 to 200 frames evenly spaced in time gives a smooth playback, showing the periodic nature of the flow. You can export the animation as a video file directly from Fluent to include it in reports or presentations. For a deeper quantitative understanding, monitor lift and drag coefficients on the cylinder during the transient simulation. You can do this by creating surface monitors for force reports and plotting them versus time. The drag coefficient will fluctuate slightly around a mean value, while the lift coefficient will oscillate with a frequency related to the vortex shedding process. From this oscillation frequency, you can calculate the Strouhal number, St, using the formula St equals Fd divided by U, where F is the shedding frequency, D is the cylinder diameter, and U is the free stream velocity. Typically, for Reynolds numbers between 100 and 10,000, the Strouhal number ranges around 0.2. Comparing your simulated value with experimental data is an excellent way to validate your CFD setup and mesh resolution. If you're studying flow-induced vibrations or aeroelastic effects, you can further couple this simulation with a dynamic mesh or a structural solver in ANSYS to analyze how the cylinder responds to these periodic lift forces. This kind of fluid structure interaction, FSI setup, allows you to observe how the oscillating pressure fields cause motion in flexible bodies, which is useful for engineering applications like bridge cables, offshore risers, or turbine blades. Once you've completed your transient simulation setup, the next crucial part is the detailed analysis of the cylinder flow behavior. This is where the real learning and engineering insights come from. The flow over a cylinder is rich in physical phenomena, including boundary layer formation, flow separation, wake development, pressure variation, and vortex shedding. Understanding each of these aspects will help you interpret CFD results meaningfully and evaluate aerodynamic characteristics accurately. Let's begin by examining the pressure distribution around the cylinder. When the fluid approaches the front face of the cylinder, it encounters a stagnation point where velocity drops to zero and pressure reaches its maximum value. This high-pressure zone represents the point of maximum resistance to flow. As the fluid moves along the curved surface of the cylinder, it accelerates due to the reduction in cross-sectional area, causing the pressure to drop according to Bernoulli's principle. The minimum pressure typically occurs near 80 to 90 degrees from the front stagnation point. Beyond this point, the boundary layer begins to lose momentum due to the adverse pressure gradient, and eventually the flow separates from the surface. This separation is responsible for the formation of the wake region behind the cylinder. In your Fluent results, you can visualize this pressure variation by plotting the pressure coefficient Cp along the cylinder's circumference. To do this, create a line around the cylinder wall and export pressure data at equal angular intervals. The Cp is calculated as where P is the free stream static pressure, RHO is the fluid density, and U is the inlet velocity. When you plot Cp versus angle, you'll typically see a sharp peak at the front, Cp approximately 1, followed by a steep drop on the sides and a sudden rise again near the rear stagnation point due to recirculating flow. Comparing this curve for laminar, turbulent, and transient cases will show how turbulence delays separation and reduces drag. Next, analyze the velocity field around the cylinder. Use contour plots or vector plots in Fluent to display the velocity magnitude. You'll notice that velocity is lowest at the front stagnation point and highest on the sides due to flow acceleration. Downstream of the separation point, there's a large region of low velocity and recirculation. This is the wake. In steady laminar simulations, the wake appears symmetrical, but in transient runs, it alternates periodically, indicating vortex shedding. To get a better view of this phenomenon, plot streamlines or path lines colored by velocity magnitude. This helps visualize how fluid particles detach, swirl, and reattach in the wake region. You can then focus on the vorticity field, which quantifies the local rotation of the fluid. Under contours, choose vorticity magnitude to display regions of rotational flow. In a transient vortex shedding regime, two distinct vortices, one rotating clockwise and the other counterclockwise, will appear alternately behind the cylinder, forming the characteristic von Karman vortex street. The spacing and intensity of these vortices depend on the Reynolds number and turbulence model used. For instance, as Reynolds number increases, vortices become more chaotic and the wake broadens. You can export vorticity data over time to track vortex evolution or even compute frequency spectra using fast Fourier transform (FFT) analysis to quantify periodic shedding behavior. Another key part of the analysis is calculating aerodynamic forces, particularly drag and lift. In Fluent, go to Reports, Forces, and select the cylinder wall as your surface. Choose the direction aligned with the flow for drag and perpendicular to it for lift. Fluent will output force values, which you can then non-dimensionalize into coefficients using the formulas and. In steady laminar flow, lift remains close to zero because the flow is symmetric, but in unsteady conditions, the lift coefficient oscillates periodically as vortices alternate from one side to the other. The drag coefficient also oscillates slightly but maintains a positive mean value. Plotting CD and CL versus time will reveal a sinusoidal lift pattern corresponding to vortex shedding cycles. From the time-dependent lift data, you can determine the vortex shedding frequency, F. Measure the time period between two consecutive lift peaks and then compute the Struhall number, ST, using. A typical value of around 0.2 indicates a physically realistic shedding behavior, confirming your simulation accuracy. This relationship between Struhall number, Reynolds number, and vortex formation is fundamental in fluid dynamics and is widely used for validation of CFD results. For more insight, perform pressure and velocity probes at specific points in the wake. By placing a monitor behind the cylinder center line, you can record time-dependent fluctuations in velocity or pressure. These signals often show periodic oscillations that match the lift coefficient frequency. Plotting these over time provides a clear visualization of how the wake oscillates between positive and negative vortices. You can even create animations of pressure or vorticity contours to show the unsteady shedding pattern in motion. This visual effect is not only educational, but also looks great for presentation or publication purposes. Another valuable post-processing step is examining drag decomposition into pressure drag and viscous drag. Fluent allows you to separate these components, showing that for bluff bodies, like a cylinder, pressure drag form drag dominates due to flow separation. By refining the mesh or introducing turbulence models that delay separation, you can observe how the total drag reduces, demonstrating how aerodynamic shaping affects performance. A deeper part of the cylinder flow analysis comes from visualizing and plotting the flow results inside ANSYS Fluent and CFD Post, which transforms your raw numerical data into physical understanding. Once your transient or steady-state simulation has converged, you can start generating graphs, contours, streamlines, and animations to interpret the behavior of the flow over the cylinder in both qualitative and quantitative terms. Begin with velocity and pressure contours. Open the Contours panel in Fluent, select velocity magnitude, and display the results over the entire flow domain. The velocity field clearly shows how the fluid slows down at the front stagnation point, accelerates over the curved sides, and drops sharply in the wake region behind the cylinder. The contours often have blue zones at the front, low velocity, and bright red streaks at the sides, high velocity, where the flow is fastest. Behind the cylinder, the wake region appears as alternating low-velocity patches in transient simulations, representing the vortices being shed periodically. You can then switch the contour variable to static pressure to observe the pressure distribution. The high-pressure area is concentrated at the stagnation point on the front face, while the rear region exhibits low pressure due to flow separation and recirculation. These pressure differences explain the net drag force acting on the cylinder. To make the flow field easier to interpret, add velocity vectors. Go to Vectors, select Velocity, and display them with appropriate scaling. The vectors illustrate the flow direction and magnitude around the cylinder and in the wake. In transient cases, you'll see vectors forming circular motion patterns behind the cylinder that change direction with time. This is direct evidence of vortex shedding. You can animate these vectors over time steps to visualize the alternating rotational motion. For clearer flow visualization, enable streamlines or path lines colored by velocity or vorticity magnitude. Streamlines show instantaneous flow structure, while path lines show the actual trajectories of fluid particles as they move over time. When you animate path lines, the alternating vortex street becomes beautifully visible, showing how the fluid separates and reattaches in cycles downstream. Once the flow field visualization is complete, move toward quantitative graph plotting to analyze physical trends. Start with the residual history plot under Monitors. This graph shows convergence behavior. The residuals of continuity and momentum should drop steadily and flatten out as the solution stabilizes. Next, create force monitors for drag and lift. Under Report Definitions, choose Forces, select the cylinder surface, and specify the direction for drag, x-axis, and lift, y-axis. Check the Plot option, so Fluent automatically graphs these values versus iteration or time step. For steady simulations, the drag coefficient will converge to a constant value, while for transient runs, the lift coefficient will oscillate periodically. This sinusoidal lift pattern corresponds directly to the frequency of vortex shedding. To compute lift and drag coefficients, CL and CD, over time, define them in Fluent's report definitions as well. You can export these plots as CSV files and use software like Excel or MATLAB for post-processing. Plotting CD and CL versus time provides a clear picture of aerodynamic forces. The average drag coefficient typically stabilizes around 1.2 for laminar flow at low Reynolds numbers, and the lift coefficient alternates around 0, with a periodic amplitude depending on flow symmetry. By performing a fast Fourier transform, FFT, on the lift signal, you can extract the vortex shedding frequency, F, and then calculate the Strohall number, St equals FD, over U. For a correctly set up cylinder case, the Strohall number usually lies between 0.18 and 0.22 for Reynolds numbers around 200. Plotting the FFT spectrum gives a sharp peak at the dominant shedding frequency, confirming periodic flow behavior. Another important visualization involves plotting pressure coefficient Cp around the cylinder surface. In Fluent, create a line from the front to the back along the cylinder wall and use surface integrals to export pressure data at multiple points along this line. Then, in a spreadsheet, compute Cp equals P minus P infinity divided by 0.5 RHOU squared and plot Cp versus angle around the cylinder 0 degrees at front, 180 degrees at rear. This plot shows how pressure drops from the stagnation point to the sides and then rises again in the separated region. Comparing this Cp distribution for laminar and turbulent simulations helps you see how turbulence delays separation and lowers drag by maintaining attached flow longer. You can also visualize vorticity and streamline patterns for a more advanced flow understanding. In Fluent's Contours menu, choose Vorticity Magnitude. Red and blue zones indicate counter-rotating vortices behind the cylinder. These contours change dynamically in transient simulations, providing an intuitive visual of the von Karman vortex street. You can create an animation sequence by selecting Graphics and Animations Create Contours and saving frames every few time steps. When you play it, you'll see alternating vortices detaching from each side, a hallmark of unsteady cylinder flow. For professional presentation, export these animations as MP4 or AVI files directly from Fluent. In addition to visualization within Fluent, you can open your case and data files in ANSYS CFD Post for more refined plotting and presentation. CFD Post allows creation of 2D and 3D plots, contour layers, and streamlines with smoother color gradients. You can also probe numerical values directly by clicking any point in the domain to read pressure, velocity, or vorticity. Under the Charts section, you can create graphs showing variable trends along specific lines or surfaces, such as velocity profile in the wake or pressure variation across a vertical line downstream of the cylinder. These plots are excellent for comparing simulated data with analytical or experimental results. To further interpret flow structure, plot Reynolds number-dependent parameters, like the drag coefficient versus Reynolds number, by running several simulations with different inlet velocities. This helps identify critical transitions in flow regimes, steady laminar flow at Re less than 40, onset of vortex shedding near Re approximately 47, periodic laminar vortices around Re equals 100 to 200, and turbulent wake beyond Re equals 1000. By plotting CD versus Re, you'll observe a gradual decline in drag coefficient with increasing Reynolds number before it sharply drops around the critical regime, demonstrating the well-known drag crisis phenomenon in fluid mechanics. Finally, use line probes to analyze velocity and pressure profiles behind the cylinder. Draw a line along the wake center line, extending a few diameters downstream. Plot velocity magnitude along this line to show how flow decelerates, reaches near zero velocity in the recirculation zone, and gradually recovers farther downstream. Similarly, plot static pressure along the same line to reveal low-pressure regions in the wake. Comparing these profiles at different time instants highlights the unsteady nature of the wake. These detailed visual and graphical analyses not only validate your CFD setup, but also give a complete physical picture of how fluid interacts with bluff bodies like cylinders. They form the foundation for studying drag reduction techniques, aerodynamic optimization, and real-world applications such as cooling tubes, chimneys, bridge cables, and offshore structures. When plotting graphs such as drag and lift coefficients, make sure to label the axes clearly and use descriptive titles for better readability. For instance, label the x-axis as time, seconds, and the y-axis as coefficient of drag, CD, or coefficient of lift, CL, depending on the plot. You can also customize the line colors and styles to differentiate multiple data sets. For example, comparing different Reynolds numbers or turbulence models. Adding a legend and grid lines enhances visual clarity, making it easier to interpret oscillation trends or steady-state behavior. In the same way, when displaying contour plots or vector fields, label the color bar with units, e.g., velocity magnitude, meters per second, or pressure, Pascal, and use a consistent color scale across all visuals to maintain uniformity. Proper labeling not only improves the presentation, but also ensures that your analysis communicates results clearly to viewers and readers. You can further enhance your flow over cylinder analysis by performing a parametric study to examine how different flow conditions affect the results. For instance, try varying the inlet velocity to simulate different Reynolds numbers. At low Reynolds numbers, the flow remains laminar and attached, showing smooth streamlines and minimal vortex formation. As you increase the velocity, the flow transitions to unsteady vortex shedding, and at even higher velocities, the wake becomes turbulent and chaotic. This variation can be visualized through drag and lift coefficient plots, revealing how aerodynamic forces evolve with changing flow regimes. Performing such studies not only helps validate your simulation setup, but also strengthens your understanding of flow physics and the influence of viscosity, pressure, and inertia on bluff body aerodynamics. Another insightful step is to analyze pressure and velocity distributions along the cylinder surface. By creating surface plots or line charts, you can measure how pressure drops from the stagnation point to the rear of the cylinder. This pressure drop directly contributes to form drag, a major factor in aerodynamic resistance. Similarly, plotting the surface shear stress helps you understand where the boundary layer separates, a critical point influencing wake formation and drag. These detailed analyses are especially useful for comparing results with analytical correlations, such as those for drag coefficients versus Reynolds numbers from empirical data. In academic or industrial applications, these comparisons validate the numerical approach and ensure that the CFD model accurately represents real-world fluid behavior. Finally, you can use animations and vector visualizations to bring your analysis to life. Create animated path lines or velocity vectors to illustrate how the flow evolves over time. Watching the vortices form, detach, and move downstream gives a dynamic sense of fluid motion that static images can't fully capture. You can also adjust transparency, streamline density, and playback speed to highlight specific features such as vortex cores, shear layers, and wake regions. These visual tools are especially powerful for presentations or reports, helping others intuitively grasp the flow behavior and patterns around the cylinder. By combining numerical data with visual storytelling, you turn your simulation into a compelling educational and analytical piece that bridges theory with practical understanding. You can further enhance your flow over cylinder analysis by expanding into a more theoretical and visual exploration of the underlying fluid behavior. When air or any fluid moves past a circular cylinder, it experiences a fascinating interaction of pressure forces, boundary layer development, and flow separation. At the front of the cylinder, the fluid particles slow down, forming a stagnation point with the highest pressure. As the fluid moves along the sides, it accelerates due to the curved surface, leading to a decrease in pressure. This is where Bernoulli's principle becomes evident. However, because of viscosity, the fluid close to the surface experiences frictional resistance, forming a thin boundary layer. Eventually, the energy within this layer becomes insufficient to overcome the adverse pressure gradient, causing the flow to separate from the surface. This separation creates a wake, a low-pressure turbulent zone behind the cylinder, which is primarily responsible for the drag force acting on it. The larger and more unstable this wake, the greater the drag. Understanding this concept in Fluent allows you to connect the numerical results with the real-world aerodynamics that influence vehicles, buildings, and industrial equipment. A detailed observation of the wake formation gives remarkable insight into fluid dynamics. In steady flow conditions at lower velocities, the wake remains symmetrical and stable behind the cylinder. As velocity increases, this symmetry breaks, and you begin to see periodic vortex shedding, alternating swirls of fluid detaching from each side of the cylinder, forming a well-known pattern called the Karaman vortex street. These vortices move downstream, creating oscillating forces on the cylinder. In practical terms, this phenomenon is crucial because it can cause vibrations in structures such as bridges, chimneys, and aircraft components. In ANSYS Fluent, transient simulation captures this unsteady behavior beautifully, allowing you to watch the evolution of vortices over time. By visualizing the flow, using path lines, you can see how the vortices form, detach, and move in a rhythmic fashion, a mesmerizing display of nature's organized chaos. Observing this dynamic motion helps in understanding why engineers must consider flow-induced vibrations in design, especially for tall or slender structures exposed to wind or fluid currents. Another important theoretical aspect is the role of pressure distribution and boundary layer behavior. Along the front of the cylinder, pressure is high and velocity is low. But as the fluid accelerates around the sides, pressure decreases while velocity rises. This imbalance between front and rear pressures creates a net drag force, known as pressure drag or form drag. In laminar flow, separation occurs early, leading to a larger wake and higher drag. In contrast, in turbulent flow, the boundary layer stays attached longer before separating, resulting in a narrower wake and reduced drag. This concept, called drag crisis, plays a critical role in aerodynamic design. For example, the dimples on a golf ball help maintain a turbulent boundary layer, delaying separation and thus reducing drag. A principle you can observe in your Fluent results when comparing different flow regimes. Through contour plots and vector diagrams, Fluent allows you to clearly see these transitions, highlighting how turbulence intensity and flow regime affect performance and efficiency. For a deeper analytical visualization, Fluent's post-processing tools make it possible to examine every detail of the simulation. You can generate color-coded contour maps showing velocity magnitude, pressure, and vorticity to highlight areas of high flow activity. Path lines and vector fields help you understand the direction and magnitude of the flow, while streamlines visualize the curvature and interaction of the fluid layers around the cylinder. Pressure contours, in particular, vividly display the front stagnation zone and low-pressure wake, giving a direct visual representation of drag-causing regions. To make your analysis more informative, you can label the color scales, adjust contour intervals, and use consistent color themes for different cases. This ensures easy comparison when you change parameters like velocity or turbulence models. Combining these visual aids with graphs of drag and lift coefficients over time paints a complete picture, one that merges quantitative results with fluid motion visuals. And with that, we conclude this immersive tutorial on flow over a cylinder using ANSYS Fluent. You've learned how to set up a simulation, observe boundary layer development, study wake formation, and interpret both steady and transient results through a mix of theory and visualization. You've also explored how turbulence, velocity, and pressure interplay to create drag and lift forces, the same principles governing everything from car aerodynamics to architectural design. Remember, the beauty of CFD lies not just in the numbers, but in the way it brings invisible fluid phenomena to life. Watching vortices dance and pressure zones shift connects simulation with physical reality in a truly captivating way. Thank you for joining us in this detailed walkthrough. This is Blueprint Bazaar, your ultimate hub for engineering learning, CAD design, and CFD simulation. Stay tuned for more tutorials. Keep exploring the science behind motion and continue to innovate fearlessly with Blueprint Bazaar, where engineering meets creativity. Please keep supporting us as we dive deeper into mechanical design and development. Don't forget to like, share, and subscribe so you never miss a step on this engineering journey with Blueprint Bazaar.